Picture this, a vast, swirling galaxy, its arms stretching across the darkness of space, dotted with stars that have burned for billions of years. Now imagine that within this seemingly infinite expanse, there are forces and mysteries so profound that even the brightest minds on Earth can't fully explain them. What if I told you that the universe, as awe-inspiring as it is, still holds secrets that defy our understanding? Welcome to a journey through 30 cosmic phenomena that continue to baffle scientists and ignite our curiosity. From the invisible grip of dark matter to the eerie silence of the Fermi Paradox, the cosmos is filled with puzzles waiting to be solved. In this video, we'll explore some of the most mind-bending mysteries of space, from the strange behavior of distant stars to the unexplained signals that might just be whispers from another civilization. By the end, you'll not only marvel at the wonders of the universe, but also realize just how much we have yet to discover. So, are you ready to dive into the unknown? Let's begin. Now turning to the first cosmic mystery on our list, dark matter. Imagine looking at the night sky and realizing that what you see, stars, galaxies, and planets, makes up only a tiny fraction of the universe. The rest, about 85% of all matter, is something we can't see, touch, or even detect directly. This invisible substance is called dark matter, and it's one of the greatest puzzles in modern science. Dark matter was first discovered not by what we could see, but by what we couldn't. In the 1930s, astronomer Fritz Zwicky noticed that galaxies in a distant cluster were moving much faster than they should have been, based on the visible matter alone. The only explanation was that there had to be some unseen mass exerting a gravitational pull, holding these galaxies together. Decades later, Vera Rubin's observations of rotating galaxies confirmed this. Stars on the outer edges were moving just as fast as those near the center, defying the laws of gravity as we understood them. The culprit, dark matter. But what exactly is dark matter? We know it doesn't emit, absorb, or reflect light, which makes it invisible to our telescopes. Yet its gravitational effects are undeniable. It shapes the large-scale structure of the universe, bending light from distant galaxies in a phenomenon called gravitational lensing. Without dark matter, galaxies would fly apart, and the cosmos as we know it wouldn't exist. Despite its importance, dark matter remains elusive. Scientists have proposed various candidates, from weakly interacting massive particles, or WIMP, to actions, but none have been definitively detected. Experiments deep underground, in space, and at particle colliders are all searching for clues, but so far, dark matter continues to hide in plain sight. The mystery of dark matter reminds us that the universe is far stranger and more complex than we can imagine. And as we continue to search for answers, we're not just uncovering the secrets of the cosmos, we're also redefining our understanding of reality itself. Now turning to the next cosmic mystery on our list, dark energy. If dark matter is the unseen glue holding the universe together, dark energy is the mysterious force pushing it apart, and doing so at an ever-increasing speed. This enigmatic energy makes up about 68% of the universe, and yet we know almost nothing about it. The story of dark energy begins in the late 1990s when astronomers made a startling discovery. By observing distant supernova, they found that the universe wasn't just expanding, it was accelerating. This was completely unexpected. According to the laws of gravity, the expansion of the universe should be slowing down over time due to the pull of matter. But instead, something was counteracting gravity, driving galaxies apart faster and faster. That something is what we now call dark energy. But what exactly is dark energy? The truth is, we don't know. One leading theory suggests it could be a property of space itself, often referred to as the cosmological constant. This idea dates back to Albert Einstein, who proposed it as a way to balance his equations of general relativity. However, Einstein later dismissed it as his greatest blunder. Ironically, it might turn out to be one of his greatest insights. Another possibility is that dark energy is a dynamic field, similar to the Higgs field, but with properties we have yet to understand. The challenge with dark energy is that it doesn't interact with light or matter in any way we can detect. It doesn't emit, absorb, or reflect anything, making it invisible to our instruments. All we can observe are its effects, the way it stretches the fabric of space and accelerates the expansion of the universe. This makes it incredibly difficult to study directly. Despite these challenges, scientists are working tirelessly to unravel the mystery of dark energy. Projects like the Dark Energy Survey and the upcoming Euclid Space Telescope aim to map the universe's expansion in unprecedented detail, hoping to shed light on this invisible force. Dark energy reminds us that the universe is not only vast but also full of surprises. It challenges our understanding of physics and forces us to rethink the very nature of reality. As we continue to explore this cosmic enigma, we're not just uncovering the secrets of the universe, we're also pushing the boundaries of human knowledge. Now turning to the next cosmic mystery on our list, the Great Attractor. Imagine a force so powerful that it's pulling entire galaxies, including our own Milky Way, toward it at incredible speeds. This mysterious gravitational anomaly, known as the Great Attractor, lies about 250 million light-years away in the direction of the constellations Centaurus and Hydra. But here's the catch: it's located in a region of the sky called the Zone of Avoidance, an area obscured by the dense dust and stars of our own galaxy. This makes studying the Great Attractor incredibly challenging, as much of it is hidden from our view. The Great Attractor was first discovered in the 1970s when astronomers noticed that galaxies in our local universe were moving in a peculiar way. Instead of spreading out evenly as the universe expands, these galaxies were being drawn toward a specific point in space. This motion defied expectations, suggesting the presence of an enormous mass exerting a gravitational pull. Estimates suggest that the Great Attractor has a mass equivalent to tens of thousands of Milky Way galaxies, making it one of the most massive structures in the known universe. But what exactly is the Great Attractor? The truth is, we're still not entirely sure. One theory suggests it could be a massive cluster of galaxies, while others propose it might be part of an even larger structure, such as the Laniakea supercluster, which encompasses our own galactic neighborhood. The problem is, the Milky Way's plane blocks our view, making it difficult to observe the Great Attractor directly. To overcome this, astronomers rely on instruments that can peer through the dust, such as radio and infrared telescopes, which reveal glimpses of the galaxies hidden behind the veil. Despite these challenges, the Great Attractor continues to captivate scientists and stargazers alike. It serves as a reminder that even in our own cosmic backyard, there are forces at work that we are only beginning to understand. As we develop new technologies and methods to study this enigmatic region, we may one day uncover the secrets of the Great Attractor and the role it plays in the grand tapestry of the universe. Now turning to another cosmic mystery that has left scientists scratching their heads: fast radio bursts, or FRB. These are incredibly brief but intense bursts of radio waves that last just milliseconds, yet they release as much energy as the sun does in an entire day. First discovered in 2007, FRBs have since been detected from various points in the universe, often billions of light-years away. What makes them so puzzling is their unpredictability. Most FRBs occur just once, while a few repeat sporadically, leaving astronomers scrambling to figure out what could possibly produce such powerful and fleeting signals. Theories about the origins of FRBs range from the plausible to the extraordinary. One leading idea is that they come from highly magnetized neutron stars known as magnetars. These dense stellar remnants, born from the explosive deaths of massive stars, can produce intense magnetic fields and emit bursts of energy that might explain FRBs. Another possibility involves cataclysmic events, such as the collision of neutron stars or black holes, which could generate these powerful radio waves. But not all explanations are so grounded in known physics. Some have even speculated that FRBs could be signals from advanced extraterrestrial civilizations, though this remains a fringe hypothesis with little evidence to support it. What makes FRBs even more intriguing is their potential to help us map the universe. As these radio waves travel across vast distances, they interact with the cosmic web of gas and dust, leaving behind subtle clues about the structure of the universe. By studying these interactions, scientists hope to learn more about the distribution of matter in the cosmos and even measure the expansion rate of the universe itself. Yet, despite their promise, FRBs remain one of the most enigmatic phenomena in astronomy, with more questions than answers. As we continue to detect and study these mysterious bursts, one thing is clear: FRBs are a reminder of how much we still have to learn about the universe. Whether they originate from exotic stellar objects or something even more extraordinary, they challenge our understanding of the cosmos and inspire us to keep searching for answers. With new telescopes and technologies coming online, the mystery of fast radio bursts may soon be unraveled, shedding light on one of the universe's most elusive secrets. Now turning to one of the most profound questions in astronomy, the Fermi Paradox. Named after physicist Enrico Fermi, this paradox highlights the puzzling contradiction between the high probability of extraterrestrial life existing in the universe and the complete lack of evidence for it. Given the sheer size of the cosmos with billions of galaxies, each containing billions of stars and planets, it seems almost certain that life should have emerged elsewhere. Yet, despite decades of searching, we have found no definitive signs of intelligent civilizations beyond Earth. One of the leading explanations for this paradox is the concept of the Great Filter. This idea suggests that there is some kind of barrier or catastrophic event that prevents life from advancing to the stage where it can communicate across interstellar distances. The Great Filter could occur at any point in the development of life. Perhaps it's incredibly rare for life to begin in the first place, or maybe civilizations tend to self-destruct before they can achieve interstellar communication. If the Great Filter lies in our past, it means we've already overcome it, and we might be among the rare few to reach our current level of advancement. But if it lies in our future, it could mean that the challenges ahead are insurmountable and civilizations like ours are destined to fail. Another possibility is that intelligent life is simply exceedingly rare. Even if life is common in the universe, the conditions required for complex, intelligent organisms to evolve might be so specific that they almost never occur. Earth's history shows that it took billions of years for life to progress from single-celled organisms to intelligent beings, and even then, it required a delicate balance of factors, from a stable climate to the right chemical ingredients. If such conditions are rare, it could explain why we haven't encountered other civilizations. Some scientists also suggest that advanced civilizations might exist but are deliberately avoiding contact with us. This idea, known as the zoo hypothesis, proposes that extraterrestrial beings might be observing us from a distance, much like we observe animals in a zoo, choosing not to interfere. Alternatively, they might be using communication methods so advanced that we simply can't detect or understand them yet. The Fermi Paradox challenges us to rethink our assumptions about life in the universe. Are we truly alone, or are we just not looking in the right way? As we continue to explore the cosmos with increasingly sophisticated tools, the answers to these questions may finally come into focus. Until then, the paradox remains a humbling reminder of how much we still have to learn about our place in the universe. Now turning to one of the most tantalizing mysteries in the search for extraterrestrial intelligence, the WOW signal. In August 1977, a radio telescope at Ohio State University detected a signal so unusual that astronomer Jerry Amon circled it on the printout and wrote, "Wow." Next to it, a name that has stuck ever since. This signal was a strong, narrowband radio burst that lasted for 72 seconds, coming from the direction of the constellation Sagittarius. What made it extraordinary was its intensity and the fact that it matched the expected characteristics of a signal from an intelligent source. The WOW signal was detected at a frequency of 1420 MHz, which is significant because it falls within the range of frequencies that are relatively quiet in space, making it an ideal listening frequency for potential extraterrestrial communication. The signal was so powerful that it stood out dramatically against the background noise, leading many to believe it could be evidence of an alien civilization attempting to make contact. However, despite numerous attempts to detect the signal again, it has never been observed since. This has left scientists puzzled and sparked decades of speculation about its origin. One theory suggests that the WOW signal could have been a natural phenomenon, such as a comet or a passing asteroid reflecting radio waves. However, no known natural source has been able to fully explain the signal's unique characteristics. Another possibility is that it was indeed a deliberate transmission from an extraterrestrial civilization, but one that was either a one-time event or directed elsewhere, making it impossible for us to detect again. The lack of a repeat signal has made it difficult to confirm its true nature, leaving it as one of the most enduring mysteries in the search for extraterrestrial intelligence. The WOW signal continues to captivate scientists and enthusiasts alike, serving as a reminder of how little we know about the universe and the potential for life beyond Earth. As our technology advances and our search for extraterrestrial signals becomes more sophisticated, perhaps one day we will finally uncover the truth behind this enigmatic event. Until then, the WOW signal remains a tantalizing clue in our quest to answer the age-old question: are we alone in the cosmos? Now turning to another cosmic enigma that has baffled astronomers and sparked the imagination of science enthusiasts worldwide: Tabby's star, also known as KIC 8462852. Discovered by the Kepler Space Telescope, this star, located approximately 1,400 light-years away in the constellation Cygnus, has become famous for its bizarre and unpredictable dimming patterns. Unlike most stars, which dim in a regular, predictable manner due to orbiting planets, Tabby's star exhibits irregular and dramatic drops in brightness, sometimes by as much as 22%. These fluctuations are so unusual that they defy conventional explanations, leading to a wide range of theories about what could be causing them. One of the most intriguing possibilities is that the dimming could be caused by alien megastructures, such as a Dyson sphere, a hypothetical construct designed by an advanced civilization to harness the energy of a star. This idea, while speculative, gained traction because the star's light patterns don't match those caused by natural phenomena like planets or dust clouds. However, other explanations have been proposed, including massive swarms of comets, interstellar dust, or even remnants of a shattered planet. Each of these theories has its own challenges, and none have been able to fully account for the star's erratic behavior. Adding to the mystery, Tabby's star has also shown long-term dimming over the years, with its overall brightness decreasing by as much as 3% between 2009 and 2013. This gradual dimming, combined with the sudden, sharp dips, has made it one of the most studied and debated objects in modern astronomy. Despite extensive observations and analysis, the true nature of Tabby's star remains elusive, leaving scientists to continue their search for answers. The mystery of Tabby's star serves as a reminder of how much we still have to learn about the universe. Whether the cause turns out to be natural or something more extraordinary, this enigmatic star challenges our understanding of stellar behavior and keeps us questioning what else might be out there. As we continue to study it, Tabby's star stands as a testament to the enduring allure of cosmic mysteries and the boundless curiosity that drives us to explore the unknown. Now turning to another cosmic mystery that puzzled scientists for decades, the pioneer anomaly. In the late 1970s and early 1980s, as the Pioneer 10 and Pioneer 11 spacecraft ventured beyond the outer planets, something strange happened. Both spacecraft experienced an unexpected and tiny but consistent deceleration that couldn't be explained by the known laws of physics. This anomaly, though small, amounting to just a fraction of a nanometer per second squared, was significant enough to challenge our understanding of gravity and motion in space. For years, scientists proposed various theories to explain this phenomenon. Some speculated that it might be evidence of new physics, such as modifications to Einstein's theory of general relativity or the influence of unseen dark matter. Others considered more exotic possibilities, like the presence of a hidden planet or even the effects of higher dimensions. The Pioneer anomaly became a hot topic in astrophysics, with researchers around the world working to uncover its cause. After decades of investigation, the mystery was finally resolved in 2012. The unexpected deceleration was traced back to a surprisingly mundane source: thermal radiation. As the spacecraft emitted heat from their power systems, the radiation exerted a tiny but measurable force, pushing back against their motion. This effect, combined with the way heat was distributed across the spacecraft, created the illusion of an unexplained deceleration. While the solution may not have been as dramatic as some had hoped, it highlighted the importance of accounting for even the smallest details in space missions. The Pioneer anomaly taught scientists valuable lessons about precision and the complexities of space exploration. It reminded us that even the most well-understood systems can harbor unexpected surprises, and that solving cosmic mysteries often requires patience, creativity, and a willingness to question our assumptions. As we continue to explore the cosmos, the lessons from the Pioneer anomaly will undoubtedly guide us in uncovering even deeper secrets of the universe. Now turning to a cosmic visitor that sparked both wonder and debate, the Oumuamua mystery. In October 2017, astronomers detected an object unlike anything they had seen before. Named Oumuamua, which means scout or messenger in Hawaiian, this interstellar traveler became the first known object from another star system to pass through our solar system. Its discovery was a historic moment, but it also raised questions that scientists are still trying to answer. Oumuamua's unusual characteristics immediately stood out. Unlike most asteroids or comets, it had an elongated, cigar-like shape, estimated to be about 10 times longer than it was wide. Even more puzzling was its motion. As it traveled through the solar system, Oumuamua exhibited a slight but unexpected acceleration that couldn't be explained by gravity alone. This behavior led to intense speculation about its origins and nature. Some scientists proposed that Oumuamua might be a comet, with outgassing the release of gas and dust causing its acceleration. However, no visible coma or tail typical of comets was observed. Others suggested it could be a fragment of a larger object, perhaps shattered by a collision or tidal forces from a distant star. But the most intriguing theory came from those who wondered if Oumuamua might be something more extraordinary, an artificial object, possibly an alien probe or spacecraft. This idea, while controversial, gained attention due to Oumuamua's peculiar shape and motion. Could it be a piece of alien technology sent to explore our solar system? While most researchers remain skeptical, the possibility has fueled discussions about how we might detect and study similar objects in the future. Oumuamua's brief visit left us with more questions than answers, challenging our understanding of interstellar objects and their potential diversity. As Oumuamua sped away, never to return, it left behind a legacy of curiosity and debate. Its discovery reminds us that the universe is full of surprises, and that even the smallest visitors can spark the biggest questions. Whether natural or artificial, Oumuamua has opened a new chapter in our exploration of the cosmos, urging us to keep looking up and wondering what else might be out there. Now turning to a cosmic mystery that challenges the very foundations of our understanding of the universe, the axis of evil. This peculiar phenomenon refers to an unexpected alignment found in the cosmic microwave background radiation, the faint afterglow of the Big Bang. Discovered in the early 2000s, this alignment has left scientists scratching their heads, as it seems to defy the principles of the standard model of cosmology. The cosmic microwave background radiation is a snapshot of the universe when it was just 380,000 years old, and it is remarkably uniform in all directions. However, when researchers analyzed the data more closely, they noticed a strange pattern. Certain fluctuations in the radiation appeared to align along a specific axis, almost as if the universe had a preferred direction. This alignment, dubbed the axis of evil, contradicts the cosmological principle which states that the universe should look the same in all directions on a large scale. The implications of this discovery are profound. If the axis of evil is real and not just a statistical fluke, it could mean that our understanding of the universe's origins and structure is incomplete. Some scientists have proposed that this alignment might be evidence of a pre-Big Bang universe, suggesting that our cosmos is part of a larger multiverse. Others speculate that it could be the result of unknown physical processes or even a sign of new physics beyond our current theories. Despite decades of study, the axis of evil remains unexplained. It serves as a reminder that even our most advanced models of the universe are still works in progress, and that the cosmos continues to surprise us with its mysteries. As we delve deeper into the cosmic microwave background and refine our observations, the axis of evil stands as a tantalizing clue that there is still much to learn about the nature of reality itself. Now turning to one of the most perplexing puzzles in modern physics, the black hole information paradox. This paradox arises from a fundamental conflict between two of our most successful theories, general relativity and quantum mechanics. According to general relativity, when matter falls into a black hole, it is lost forever, crushed into the singularity at the center. But quantum mechanics tells us that information cannot be destroyed. It must be preserved, even if it's scrambled or transformed. So, what happens to the information that falls into a black hole? This question has baffled scientists for decades. The paradox became particularly prominent after Stephen Hawking proposed that black holes emit radiation, now known as Hawking radiation. This radiation is thought to cause black holes to slowly lose mass and eventually evaporate. But here's the problem. Hawking radiation appears to be random, carrying no information about the matter that fell into the black hole. If the black hole evaporates completely, where does the information go? This seems to violate the principles of quantum mechanics, which insist that information must always be conserved. To resolve this paradox, physicists have proposed several intriguing theories. One of the most prominent is the holographic principle, which suggests that all the information about the matter that falls into a black hole is encoded on its event horizon, the boundary beyond which nothing can escape. This idea implies that the universe might function like a hologram, with a two-dimensional surface encoding all the information about a three-dimensional space. Another theory involves the idea that information might escape through Hawking radiation in a highly scrambled form, making it nearly impossible to decode but still technically preserved. Despite these theories, the black hole information paradox remains unsolved. It challenges our understanding of the fundamental laws of physics and forces us to rethink the nature of space, time, and information itself. As we continue to explore the mysteries of black holes, this paradox serves as a reminder that the universe is far stranger and more complex than we can currently comprehend. And with each new discovery, we inch closer to unraveling one of the greatest enigmas of the cosmos. Now turning to another cosmic mystery that has left scientists scratching their heads, the Hubble tension. This phenomenon revolves around a puzzling discrepancy in how fast the universe is expanding. For decades, astronomers have used two primary methods to measure the universe's expansion rate, known as the Hubble constant. The first method involves observing distant supernovae and measuring their brightness to calculate distances. The second method relies on the cosmic microwave background radiation, the faint afterglow of the Big Bang, which provides a snapshot of the early universe. Here's where things get strange. These two methods, which should theoretically agree, give us different results. Observations of supernovae suggest a faster expansion rate, while measurements from the cosmic microwave background point to a slower one. This inconsistency, known as the Hubble tension, has become one of the most significant challenges in modern cosmology. It's not just a small discrepancy, it's a gap that suggests our understanding of the universe might be missing something fundamental. So, what could be causing this tension? One possibility is that there's an unknown ingredient in the universe, something we haven't yet detected or accounted for. This could be a new form of dark energy, a mysterious force driving the universe's accelerated expansion, or even an undiscovered particle influencing cosmic evolution. Another possibility is that our current models of physics are incomplete, and we need to revise our understanding of gravity or the behavior of space and time on cosmic scales. The implications of the Hubble tension are profound. If it points to new physics, it could revolutionize our understanding of the universe, much like the discovery of dark energy did in the late 1990s. It could also mean that our current measurements are being affected by some unseen systematic error, though extensive efforts to rule out such errors have so far come up empty-handed. As scientists continue to refine their measurements and explore new theories, the Hubble tension remains a tantalizing mystery. It challenges us to question what we think we know about the cosmos and pushes us to uncover deeper truths about the nature of reality. And as we delve further into this cosmic puzzle, we may find that the universe has even more surprises in store for us. Now turning to another cosmic enigma that has puzzled astronomers for years, the Kuiper Cliff. Beyond the Kuiper belt, a region of icy bodies and dwarf planets like Pluto, lies a mysterious boundary where the number of objects suddenly drops off. This abrupt decline, known as the Kuiper Cliff, defies our expectations. Based on our understanding of the solar system's formation, we would expect to find a gradual decrease in objects as we move farther out. Instead, the Kuiper Cliff presents a sharp and unexpected edge, leaving scientists searching for answers. What could be causing this sudden drop-off? One leading theory suggests the presence of an undiscovered planet, often referred to as Planet 9 or Planet X. This hypothetical world, thought to be several times the mass of Earth, could be lurking in the distant reaches of the solar system. Its gravitational influence might have swept the area clean, pushing objects out of their orbits and creating the observed cliff. While no direct evidence of such a planet has been found yet, its existence would explain not only the Kuiper Cliff, but also the peculiar orbits of some distant objects in the Kuiper belt. Another possibility is that gravitational interactions with passing stars or other massive objects in the galaxy's history could have disrupted the outer regions of the Kuiper belt. Over billions of years, these disturbances might have scattered objects away, leaving behind the sharp boundary we see today. Alternatively, the Kuiper Cliff could be a remnant of the solar system's early days, a relic of the chaotic processes that shaped our cosmic neighborhood. The Kuiper Cliff challenges our understanding of the solar system's structure and evolution. It raises questions about what lies beyond this boundary and whether our current models of planetary formation are complete. As astronomers continue to explore the outer reaches of the solar system, the search for answers to this mystery could lead to groundbreaking discoveries, reshaping our knowledge of the cosmos and our place within it. Now turning to another cosmic puzzle that has left scientists scratching their heads, the missing baryon problem. Baryonic matter, the ordinary stuff that makes up stars, planets, and even us, should be everywhere in the universe. Based on our calculations of the Big Bang and the formation of the cosmos, there's a significant amount of this matter that we simply can't find. It's like a cosmic game of hide and seek, and the universe is winning. So, where is all this missing baryonic matter hiding? One leading theory suggests it's woven into the fabric of the cosmic web, the vast network of filaments that connect galaxies across the universe. These filaments are thought to be filled with hot, diffuse gas, too faint to detect with traditional telescopes. This gas, often referred to as the warm hot intergalactic medium, could be the key to solving the mystery. But detecting it is no easy task. It requires cutting-edge technology and innovative methods, like observing the way light from distant quasars passes through these filaments, leaving behind subtle clues in their spectra. Another possibility is that some of this missing matter exists in the form of faint, low-mass stars or rogue planets drifting through the darkness of interstellar space. These objects, too dim to be easily spotted, could be scattered throughout galaxies, contributing to the overall baryonic count. Yet, even with these explanations, a significant portion of the missing matter remains unaccounted for, pushing scientists to explore even more exotic possibilities. The missing baryon problem isn't just a curiosity, it's a fundamental challenge to our understanding of the universe's composition. If we can't account for all the ordinary matter, how can we hope to fully grasp the nature of dark matter and dark energy, which make up the vast majority of the cosmos? Solving this mystery could unlock new insights into the structure and evolution of the universe, bringing us one step closer to understanding the grand tapestry of existence. As astronomers continue to refine their tools and techniques, the search for the missing baryons remains a thrilling frontier in modern astrophysics. Now turning to another cosmic enigma that challenges our understanding of the universe, the Eridanus supervoid. This vast region of space, stretching over hundreds of millions of light-years, is eerily empty compared to the rest of the cosmos. While most areas of the universe are teeming with galaxies, clusters, and cosmic structures, the Eridanus supervoid stands out as a colossal blank spot, a place where galaxies are few and far between. But what makes this supervoid even more intriguing is its potential connection to one of the most puzzling features in the cosmic microwave background, the cold spot. The cold spot is a mysterious region in the afterglow of the Big Bang, where the temperature is slightly lower than the surrounding areas. For years, scientists have debated its origin. Could the Eridanus supervoid be the key to solving this mystery? One theory suggests that the supervoid's immense emptiness might be causing the cold spot. As light from the cosmic microwave background passes through the supervoid, it loses energy due to the expansion of space, a phenomenon known as the integrated Sachs-Wolf effect. This energy loss could explain why the cold spot appears cooler than its surroundings. However, not everyone is convinced. Some researchers argue that the supervoid isn't large enough or empty enough to fully account for the cold spot's temperature drop. This has led to alternative explanations, including the possibility of a collision with another universe or the presence of exotic physics beyond our current understanding. The debate continues, and the Eridanus supervoid remains a tantalizing piece of the puzzle. What makes this phenomenon so fascinating is its potential to reshape our understanding of the universe's large-scale structure. If the supervoid is indeed linked to the cold spot, it could provide new insights into the nature of cosmic voids and their role in the evolution of the cosmos. On the other hand, if the connection proves elusive, it might hint at entirely new physics waiting to be discovered. As astronomers continue to study this enigmatic region, the Eridanus supervoid serves as a reminder of how much we still have to learn about the vast, mysterious expanse of space. Now turning to another cosmic mystery that defies our expectations, the boötes void. Known as one of the largest voids in the observable universe, this immense region of space spans an astonishing distance of around 330 million light-years. To put that into perspective, if you were to place the Milky Way at one end of the boötes void, you'd need to travel an unimaginable distance before encountering another galaxy. This vast emptiness is so extreme that it has earned the nickname the Great Nothing. But what makes the boötes void so perplexing? Unlike the Eridanus supervoid, which still contains some galaxies, the boötes void is almost entirely devoid of them. Scientists estimate that it houses only about 60 galaxies, a staggeringly low number compared to the thousands that would typically occupy a space of this size. This extreme sparsity challenges our understanding of how matter is distributed across the universe. According to the standard model of cosmology, matter should be spread relatively evenly, with galaxies forming clusters and filaments separated by smaller voids. The boötes void, however, breaks this pattern, presenting a cosmic anomaly that raises more questions than answers. One of the biggest challenges in explaining the boötes void lies in its sheer size and emptiness. How did such a massive region of space end up with so little matter? Some theories suggest that it could be the result of smaller voids merging over billions of years, creating a supervoid of unprecedented scale. Others propose that it might be linked to the early universe, where fluctuations in density during the Big Bang left behind regions of extreme emptiness. Yet, none of these explanations fully account for the void's extraordinary characteristics. The boötes void also has profound implications for our understanding of the universe's large-scale structure. If voids like this are more common than we think, they could significantly influence the way galaxies and galaxy clusters form and evolve. They might even play a role in the mysterious forces shaping the cosmos, such as dark energy. However, studying the boötes void is no easy task. Its immense size and lack of observable features make it a difficult target for astronomers, who must rely on indirect methods to map its structure and properties. As we continue to explore this cosmic enigma, the boötes void serves as a humbling reminder of how much we still don't know about the universe. Its existence challenges our assumptions and pushes the boundaries of our knowledge, urging us to rethink the very fabric of reality. What other secrets might this vast emptiness hold, and what could it teach us about the origins and fate of the cosmos? The answers, much like the void itself, remain shrouded in mystery. Now turning to another cosmic puzzle that has left scientists scratching their heads, the cosmic lithium problem. When we look at the universe, we expect to see certain amounts of elements like hydrogen, helium, and lithium based on what we know about the Big Bang. According to the theory of Big Bang nucleosynthesis, the early universe should have produced a specific amount of lithium as it cooled and expanded. However, when astronomers measure the lithium content in the oldest stars and gas clouds, they find only about 1/3 of what the theory predicts. This glaring discrepancy is known as the cosmic lithium problem, and it challenges our understanding of how the universe formed and evolved. So, why does this matter? Lithium is one of the lightest elements, and its abundance is a key piece of evidence for testing our models of the early universe. If our predictions are off, it could mean there's something fundamentally missing in our understanding of the Big Bang. One possibility is that our models of nucleosynthesis, the process by which elements formed in the first few minutes after the Big Bang, are incomplete. Perhaps there were unknown physical processes at play that destroyed or altered lithium over time. Another theory suggests that lithium might have been absorbed or transformed by stars, though this doesn't fully explain the observed shortfall. The cosmic lithium problem also raises questions about the conditions of the early universe. If the amounts of hydrogen and helium match our predictions, why doesn't lithium? Could there have been fluctuations in temperature or density that affected lithium production? Or is there something about the way stars process lithium that we don't yet understand? These questions highlight the complexity of the universe's chemical history and remind us that even the simplest elements can hold profound mysteries. As researchers continue to investigate this problem, They're exploring new avenues, such as studying the atmospheres of ancient stars and analyzing the light from distant quasars to measure lithium levels more accurately. Each discovery brings us closer to solving this cosmic riddle, but for now, the cosmic lithium problem remains a tantalizing reminder of how much we still have to learn about the universe's origins. What other secrets might the early universe be hiding, and how might solving this mystery reshape our understanding of the cosmos? The answers, like the lithium itself, are still waiting to be uncovered. Now turning to another cosmic enigma that has puzzled astronomers for decades, the galactic center excess. At the heart of our Milky Way galaxy, there's a strange and intense glow of gamma-ray radiation that defies easy explanation. This mysterious emission, known as the galactic center excess, was first detected by space telescopes like Fermi, and it has since become one of the most intriguing puzzles in modern astrophysics. So, what's causing this excess gamma-ray radiation? One leading theory points to dark matter, the elusive substance that makes up most of the universe's mass but has never been directly observed. According to this idea, dark matter particles could be colliding and annihilating each other near the galactic center, releasing gamma rays in the process. If true, this would be a groundbreaking discovery, offering the first indirect evidence of dark matter's existence. However, not everyone is convinced. Another possibility is that the gamma rays are coming from a dense population of pulsars rapidly spinning neutron stars that emit powerful beams of radiation. These pulsars could be clustered in the galactic center, creating the observed excess. Yet, even this explanation has its challenges. The number of pulsars required to produce such a signal seems unusually high, and so far, astronomers haven't found enough of them to fully account for the phenomenon. The mystery deepens when we consider the complexity of the galactic center itself. This region is packed with stars, gas clouds, and other energetic objects, making it difficult to isolate the source of the gamma rays. Could there be a combination of factors at play, or is there an entirely new astrophysical process we haven't yet discovered? As scientists continue to study the galactic center excess, they're using advanced telescopes and simulations to untangle this cosmic puzzle. Each new observation brings us closer to understanding what's happening at the heart of our galaxy. But for now, the galactic center excess remains a tantalizing mystery, reminding us that even the most familiar parts of the universe can hold surprises. What will we uncover next about the Milky Way's hidden secrets? The answers may lie in the very heart of our cosmic home. Now turning to a pivotal chapter in the universe's history, we explore the reionization era, a time when the cosmos underwent a dramatic transformation. After the Big Bang, the universe was a dark, dense soup of hydrogen gas. But as the first stars and galaxies began to form, they ignited a cosmic revolution, flooding the universe with light and energy. This process, known as reionization, marked the end of the so-called cosmic dark ages and set the stage for the universe we see today. So, what exactly happened during this era? As the first stars and galaxies emerged, their intense ultraviolet radiation began to ionize the surrounding hydrogen gas, stripping electrons from atoms and turning the once neutral hydrogen into a sea of charged particles. This reionization process didn't happen all at once. It unfolded over hundreds of millions of years, gradually lighting up the universe. But understanding this era is no easy task. One of the biggest challenges is that the first stars and galaxies are incredibly faint and distant, making them difficult to observe directly. Astronomers rely on indirect clues, such as the light from ancient quasars, to piece together what happened. These quasars act like cosmic flashlights, illuminating the gas clouds that existed during reionization and revealing how the universe transitioned from darkness to light. Another mystery is the role of early galaxies in this process. Were they the primary drivers of reionization, or did other sources like black holes or even dark matter play a significant role? Current evidence suggests that galaxies were the main contributors, but the exact details remain unclear. How many galaxies were needed to fully ionize the universe? And how did their formation and evolution influence the pace of reionization? The reionization era is a crucial piece of the cosmic puzzle, bridging the gap between the early universe and the vibrant cosmos we see today. As scientists continue to study this period using cutting-edge telescopes and simulations, they hope to uncover more about the first stars, galaxies, and the forces that shaped our universe. What secrets will we uncover about this transformative era? The answers could rewrite our understanding of cosmic history. Now turning to another cosmic mystery that challenges our understanding of the universe, we encounter the quasar alignment. Quasars, the incredibly bright cores of distant galaxies powered by supermassive black holes, are scattered across the cosmos. Yet, astronomers have discovered something astonishing. Some quasars, separated by billions of light years, appear to be aligned in a way that defies the cosmological principle. This principle states that, on a large scale, the universe should look the same in all directions, with no preferred orientation. But the alignment of these quasars suggests there might be more to the story. Imagine looking at a vast cosmic web where threads of galaxies and quasars stretch across the universe. In this web, certain quasars seem to point in the same direction, as if influenced by some unseen force or structure. This alignment isn't just a coincidence, it's a puzzle that has left scientists scratching their heads. How can objects so far apart with no apparent connection share such a striking alignment? Could there be a larger, undiscovered structure in the universe guiding their orientation? Or does this hint at a flaw in our current understanding of cosmic evolution? The implications of this discovery are profound. If the cosmological principle doesn't hold true on such vast scales, it could mean our understanding of the universe's structure is incomplete. It might suggest the presence of cosmic filaments or other large-scale structures that influence the alignment of quasars. Alternatively, it could point to new physics, such as exotic forces or fields that operate on scales we've yet to comprehend. Whatever the explanation, the quasar alignment forces us to rethink our assumptions about the universe's uniformity and the forces that shape it. As astronomers continue to study these enigmatic alignments, they hope to uncover clues about the universe's large-scale structure and the forces at play. Could this discovery lead us to a deeper understanding of cosmic evolution, or will it remain one of the universe's most perplexing mysteries? The answers may lie hidden in the light of these distant quasars waiting to be revealed. Now turning to another fascinating cosmic puzzle, we delve into the neutrino mass mystery. Neutrinos, often called ghost particles, are among the most elusive and abundant particles in the universe. For decades, scientists believed they were massless, as predicted by the standard model of particle physics. But in the late 1990s, a groundbreaking discovery turned this assumption on its head. Neutrinos do, in fact, have mass. This revelation came from observations of neutrino oscillations, a phenomenon where neutrinos change their type or flavor as they travel through space. For this to happen, neutrinos must have mass, albeit an incredibly tiny amount. This discovery was a seismic shift in our understanding of particle physics, as it directly contradicted the standard model, which had long been the cornerstone of our knowledge about the fundamental building blocks of the universe. The implications of this discovery are far-reaching. If neutrinos have mass, they could play a significant role in the universe's evolution, influencing everything from the formation of galaxies to the balance of matter and antimatter. Their tiny mass also makes them a potential candidate for dark matter, the mysterious substance that makes up a significant portion of the universe's mass but remains invisible to us. However, neutrinos are far too light to account for all of dark matter, leaving scientists to wonder what other particles or forces might be at play. The neutrino mass mystery also opens the door to new physics beyond the standard model. It suggests that there are still fundamental aspects of the universe we don't fully understand, and that our current theories may need to be revised or expanded. Researchers are now racing to measure the exact masses of neutrinos and understand how they interact with other particles. These efforts could lead to breakthroughs in our understanding of the universe's most fundamental laws. As we continue to probe the secrets of neutrinos, we are reminded of how much we still have to learn about the cosmos. These ghostly particles, once thought to be massless, now challenge our understanding of reality itself. Could solving the neutrino mass mystery unlock new insights into the universe's deepest secrets? The answer may lie in the delicate dance of these elusive particles, waiting to be uncovered by the next generation of experiments. Now turning to another cosmic enigma, we explore the cosmic ray anomaly. Cosmic rays are high-energy particles that travel through space at nearly the speed of light, bombarding Earth from all directions. While most cosmic rays originate from sources like supernova or the Sun, scientists have detected an unexplained excess of ultra-high-energy cosmic rays that defy our current understanding of astrophysics. These mysterious particles carry energies millions of times greater than those produced in the most powerful particle accelerators on Earth. Their origins remain a puzzle, as no known astrophysical process can easily explain how they achieve such extreme energies. Some theories suggest they might come from supermassive black holes, active galactic nuclei, or even the decay of exotic dark matter particles. Yet none of these explanations fully account for the observed patterns and intensities of these cosmic rays. Adding to the mystery is the fact that these ultra-high-energy cosmic rays are incredibly rare. Detecting them requires massive observatories like the Pierre Auger Observatory in Argentina, which spans an area the size of Rhode Island. Even with such advanced technology, pinpointing their exact sources has proven elusive. The particles are deflected by magnetic fields as they travel through space, making it nearly impossible to trace them back to their points of origin. The cosmic ray anomaly also raises questions about the limits of our understanding of particle physics. How do these particles reach such staggering energies? Could they be evidence of new, undiscovered physical processes or particles? Some researchers speculate that they might be linked to phenomena like cosmic strings or even the remnants of the Big Bang itself. However, without more data, these ideas remain speculative. As scientists continue to study these enigmatic particles, they are reminded of how much we still don't know about the universe. The cosmic ray anomaly challenges our understanding of the cosmos, pushing us to rethink the boundaries of physics and astronomy. Could solving this mystery reveal new insights into the universe's most extreme environments? The answer may lie in the next breakthrough observation or experiment, waiting to shed light on these high-energy cosmic travelers. Now turning to another celestial marvel, we encounter the Red Rectangle Nebula, a striking and mysterious structure that has puzzled astronomers for decades. Located about 2,300 light-years away in the constellation Monoceros, this nebula stands out for its unique geometric shape and vivid red hues. Unlike most nebulae, which appear as swirling clouds or irregular blobs, the red rectangle boasts a nearly perfect rectangular form, with a series of ladder-like rungs extending outward from its center. This unusual structure has earned it the nickname the Cosmic Ladder. The red rectangle's vibrant colors are equally fascinating. Its deep red glow is caused by a process called fluorescence, where ultraviolet light from the central star excites hydrogen molecules, causing them to emit light in the red part of the spectrum. However, the exact mechanisms behind its intricate shape and the distribution of its colors remain a mystery. Scientists believe that the nebula's formation is closely tied to the presence of a binary star system at its heart. These two stars, orbiting each other in a tight dance, are thought to have ejected material in a way that created the nebula's distinctive structure. One of the biggest challenges in understanding the red rectangle is explaining how such a precise geometric shape could form naturally. Most nebulae are shaped by chaotic processes like stellar winds or supernova explosions, but the red rectangle's symmetry suggests a more orderly origin. Some theories propose that the binary star's gravitational interactions and the way they expel material could create the ladder-like rungs. Others suggest that the nebula's shape might be influenced by a dense disk of dust and gas surrounding the stars, which channels the outflowing material into the rectangular pattern we observe. Despite these theories, many questions remain unanswered. Why does the red rectangle appear so different from other nebulae? What role do the binary stars play in shaping its structure, and how do they produce such a vivid red glow? Observations using advanced telescopes like the Hubble Space Telescope have provided stunning images of the nebula, but they have also revealed new layers of complexity, such as intricate patterns of dust and gas that defy simple explanations. The Red Rectangle Nebula serves as a reminder of the universe's endless capacity to surprise us. Its beauty and mystery challenge our understanding of how stars and nebulae evolve, offering a glimpse into the intricate processes that shape the cosmos. As astronomers continue to study this enigmatic object, they hope to uncover the secrets behind its formation and perhaps even learn more about the role of binary stars in sculpting the universe's most stunning structures. Could the red rectangle hold clues to other cosmic mysteries? The answers may lie hidden within its glowing red rungs, waiting to be discovered. Now turning to another cosmic enigma, we encounter the Hercules Corona Borealis Great Wall, one of the largest known structures in the universe. Discovered in 2013, this colossal formation stretches over an astonishing 10 billion light-years, making it a true giant among cosmic structures. To put that into perspective, it's so vast that it challenges our understanding of the universe's large-scale structure and even calls into question the cosmological principle, which states that the universe should look roughly the same in all directions on a large scale. The Hercules Corona Borealis Great Wall is essentially a massive concentration of galaxies, galaxy clusters, and other cosmic matter, forming a filament-like structure that defies expectations. Its sheer size and density are difficult to reconcile with current models of the universe's evolution. According to these models, structures of this magnitude shouldn't exist, as the universe hasn't had enough time since the Big Bang for such a massive formation to come together. Yet there it is, a cosmic behemoth that forces us to rethink our assumptions. One of the most intriguing aspects of this structure is how it was discovered. Astronomers identified it by mapping the distribution of gamma-ray bursts, which are incredibly energetic explosions that occur in distant galaxies. These bursts serve as cosmic signposts, marking the locations of galaxies and galaxy clusters. By analyzing their distribution, scientists were able to trace the outline of the Hercules Corona Borealis Great Wall, revealing its staggering scale. The existence of such a massive structure has profound implications for cosmology. It suggests that there may be even larger structures out there, waiting to be discovered, and that our current understanding of the universe's large-scale structure might be incomplete. Some scientists speculate that the Hercules Corona Borealis Great Wall could be a remnant of an earlier phase of the universe, a relic from a time when the cosmos was much denser and more chaotic. Others propose that it might be evidence of new physics, hinting at forces or processes we have yet to uncover. As we continue to explore the universe, the Hercules Corona Borealis Great Wall stands as a testament to the mysteries that still await us. Its discovery reminds us that the cosmos is far more complex and wondrous than we can imagine, and that every new observation has the potential to reshape our understanding of reality. Could this colossal structure be just the beginning of a new chapter in cosmology? The answers may lie in the distant reaches of space, where even greater wonders await discovery. Now turning to another cosmic mystery, we delve into the cold spot in the cosmic microwave background, a peculiar region that has puzzled scientists for years. The cosmic microwave background, or CMB, is the afterglow of the Big Bang, a faint radiation that fills the universe and provides a snapshot of its early conditions. Within this radiation, there exists a cold spot, an area significantly cooler than its surroundings, and its existence challenges our understanding of the universe's structure and evolution. The cold spot was first detected by the Wilkinson Microwave Anisotropy Probe, or WMAP, and later confirmed by the Planck satellite. It spans a vast region of space, roughly 1.8 billion light-years across, and its temperature is about 70 microkelvin cooler than the average CMB temperature. At first glance, such a fluctuation might seem like a random anomaly, but the cold spot's size and significance make it far more intriguing. One of the leading theories to explain the cold spot is the existence of a supervoid, an enormous region of space with far fewer galaxies and matter than expected. If such a void exists, it could cause the CMB radiation passing through it to lose energy, creating the observed temperature drop. However, the sheer size of the cold spot makes this explanation challenging. The void required to produce such an effect would need to be improbably large, stretching the limits of our current cosmological models. Another, more speculative theory suggests that the cold spot could be evidence of a collision with another universe. According to this idea, our universe might have bumped into a neighboring one during its early expansion, leaving behind a kind of cosmic bruise in the form of the cold spot. While this theory is highly controversial and lacks direct evidence, it highlights the profound implications the cold spot could have for our understanding of the multiverse and the nature of reality itself. The cold spot remains one of the most tantalizing mysteries in cosmology. Its existence forces us to question whether it's a statistical fluke, a sign of new physics, or even a window into a multiverse. As we continue to study the CMB and refine our observations, the cold spot serves as a reminder that the universe is full of surprises, and that even the faintest whispers of radiation can hold the keys to unlocking its deepest secrets. What other cosmic anomalies might be hiding in the vast expanse of space, waiting to challenge our understanding of the cosmos? The answers may lie just beyond the next observation. Now turning to another cosmic enigma, we explore the mystery of the missing magnetic monopoles, according to grand unified theories which aim to combine the fundamental forces of nature into a single framework. Magnetic monopoles should exist. These hypothetical particles are essentially isolated magnetic charges, akin to the positive and negative charges of electricity, but for magnetism. Yet, despite decades of searching, no magnetic monopole has ever been detected, leaving scientists puzzled and questioning the validity of these theories. The concept of magnetic monopoles arises from the idea that in the early universe, as temperatures and energies were incredibly high, the fundamental forces were unified. As the universe cooled and expanded, these forces separated, and in the process, magnetic monopoles should have been created in abundance. However, their absence in the observable universe poses a significant challenge to our understanding of particle physics and cosmology. One possible explanation for the missing monopoles is inflation, a rapid expansion of the universe that occurred just moments after the Big Bang. Inflation could have diluted the density of monopoles to such an extent that they became virtually undetectable. While this theory aligns with other cosmological observations, it doesn't fully resolve the issue, as some monopoles should still exist in detectable quantities. Another intriguing possibility is that monopoles are simply too massive or too rare to be observed with current technology. If they exist at all, they might be hiding in regions of space we have yet to explore or require more advanced detection methods to uncover. The search for monopoles continues, with experiments like those conducted at the Large Hadron Collider and specialized detectors designed to capture even the faintest traces of these elusive particles. The absence of magnetic monopoles has profound implications for our understanding of the universe. If they are never found, it could mean that grand unified theories need to be revised or that our understanding of the early universe is incomplete. On the other hand, their discovery would revolutionize particle physics, providing direct evidence for the unification of forces and opening new avenues for exploring the fundamental nature of reality. As we continue to probe the mysteries of the cosmos, the search for magnetic monopoles reminds us that even the most well-founded theories can be challenged by the universe's complexities. What other hidden particles or forces might be waiting to be discovered, reshaping our understanding of the fabric of existence? The answers lie in the relentless pursuit of knowledge, one observation at a time. Now turning to another perplexing cosmic mystery, we delve into the galaxy rotation problem, a phenomenon that has baffled astronomers for decades. When scientists observe how galaxies rotate, they find something unexpected. The outer regions of galaxies spin much faster than predicted by the visible matter alone. According to the laws of gravity, stars and gas on the outskirts of a galaxy should move slower, much like planets farther from the Sun. But observations show that these outer regions rotate at nearly the same speed as the inner parts, defying our expectations. This discrepancy between what we see and what we predict has led to one of the most compelling pieces of evidence for dark matter. Dark matter, an invisible and mysterious substance that does not emit, absorb, or reflect light, is thought to make up a significant portion of the universe's mass. Its gravitational influence could explain why galaxies rotate the way they do. The idea is that dark matter forms a vast, invisible halo around galaxies, providing the extra gravitational pull needed to keep the outer regions spinning at such high speeds. The galaxy rotation problem was first highlighted in the 1970s when astronomer Vera Rubin and her colleagues studied the rotation curves of spiral galaxies. Their observations revealed that stars and gas in the outer parts of galaxies were moving far too quickly to be accounted for by the visible matter alone. This discovery was a turning point in astrophysics, as it provided strong evidence that something unseen dark matter was at play. Despite the compelling case for dark matter, its exact nature remains one of the greatest unsolved mysteries in science. While it explains the galaxy rotation problem beautifully, dark matter has yet to be directly detected. Scientists have proposed various candidates for dark matter particles, such as weakly interacting massive particles or WIMP, but so far, none have been conclusively observed. Experiments deep underground and in space continue to search for these elusive particles, hoping to shed light on this cosmic enigma. The galaxy rotation problem not only highlights the limitations of our current understanding of gravity and matter, but also underscores the vastness of what we have yet to discover. If dark matter is indeed the key to solving this mystery, its detection would revolutionize our understanding of the universe, confirming the existence of a hidden cosmic framework that shapes the behavior of galaxies. Until then, the galaxy rotation problem remains a tantalizing reminder of how much we still have to learn about the cosmos. What other secrets might the universe be hiding, waiting for us to uncover? The journey to find out continues, one observation at a time. Now turning to another fascinating cosmic puzzle, we explore the lyman-alpha forest, a phenomenon that reveals the intricate structure of the universe on the largest scales. When astronomers observe the light from distant quasars, extremely bright objects powered by supermassive black holes, they notice something peculiar. The light is not smooth, but instead marked by a series of dark absorption lines. These lines, known as the lyman-alpha forest, are caused by clouds of hydrogen gas scattered throughout the vast expanses of space between galaxies. The lyman-alpha forest acts like a cosmic fingerprint, encoding information about the distribution and properties of hydrogen in the intergalactic medium. As light from a quasar travels through space, it passes through these hydrogen clouds, which absorb specific wavelengths of light corresponding to the lyman-alpha transition of hydrogen. Each cloud leaves its own unique imprint, creating a forest of absorption lines in the quasar's spectrum. By studying these lines, scientists can map the large-scale structure of the universe, tracing the web-like network of gas that connects galaxies and holds clues to the universe's evolution. One of the most remarkable aspects of the lyman-alpha forest is its ability to provide a timeline of the universe's history. Because light takes time to travel, observing quasars at different distances allows astronomers to peer back in time, seeing how the intergalactic medium has changed over billions of years. This has revealed that the universe was once a much denser and more chaotic place, with hydrogen gas gradually becoming more diffuse as galaxies formed and evolved. However, modeling the lyman-alpha forest is no easy task. The complex interplay of factors, such as the temperature, density, and ionization state of the gas, as well as the effects of cosmic expansion and gravitational interactions, makes it a challenging puzzle to solve. Supercomputer simulations are often used to recreate the conditions of the early universe and predict how the lyman-alpha forest should appear. Yet, discrepancies between these models and observations continue to push scientists to refine their understanding of the intergalactic medium and the forces shaping it. The lyman-alpha forest not only deepens our understanding of the universe's structure, but also serves as a powerful tool for testing theories of cosmology and galaxy formation. It reminds us that even the seemingly empty spaces between galaxies are teeming with activity, offering a wealth of information for those who know how to look. As we continue to unravel the mysteries of the lyman-alpha forest, we gain new insights into the cosmic web that binds the universe together, revealing the hidden threads of its grand design. What other secrets might these ancient clouds of hydrogen hold, waiting to be uncovered? The search for answers continues, one quasar at a time. Now turning to another cosmic enigma, we delve into the mystery of ultra-high-energy cosmic rays, particles that arrive at Earth with energies so immense they defy our current understanding of physics. These cosmic rays, which are mostly protons or atomic nuclei, travel through space at nearly the speed of light, carrying energies millions of times greater than those produced by the most powerful particle accelerators on Earth. The sheer magnitude of their energy raises a fundamental question. What cosmic events could possibly generate such extraordinary particles? The detection of ultra-high-energy cosmic rays is a feat in itself. When these particles collide with Earth's atmosphere, they create cascades of secondary particles, producing faint flashes of light that can be detected by specialized observatories. One of the most famous facilities for studying these cosmic rays is the Pierre Auger Observatory in Argentina, which uses an array of detectors spread over thousands of square kilometers to capture these rare and fleeting events. Despite these advanced tools, pinpointing the exact sources of ultra-high-energy cosmic rays remains a significant challenge. One of the biggest puzzles is that these particles should not be able to travel vast distances through space without losing energy. According to our current understanding, interactions with the cosmic microwave background radiation, the faint afterglow of the Big Bang should slow them down over long distances. Yet, ultra-high-energy cosmic rays are observed arriving from directions that suggest they have traveled across billions of light years. This contradiction has led scientists to propose that these particles might originate from relatively nearby sources, such as active galactic nuclei, gamma-ray bursts, or even more exotic phenomena like supermassive black holes or cosmic strings. However, no definitive source has been identified, leaving this mystery unsolved. The implications of ultra-high-energy cosmic rays extend far beyond their origins. Their existence challenges our understanding of particle physics and the fundamental forces of nature. If these particles are indeed produced by extreme cosmic events, studying them could provide insights into the most energetic processes in the universe, from the birth of black holes to the collisions of entire galaxies. Moreover, they could help us test the limits of the standard model of particle physics. potentially revealing new particles or forces that we have yet to discover. As we continue to search for the sources of ultra-high-energy cosmic rays, we are reminded of the universe's capacity to surprise and challenge us. These particles, born in the most violent and energetic corners of the cosmos, carry with them the secrets of the universe's most extreme environments. What new discoveries await us as we unravel the mysteries of these cosmic messengers? The quest to understand ultra-high-energy cosmic rays is far from over, and each detection brings us one step closer to uncovering the truth. Now turning to one of the most mind-bending concepts in modern cosmology, we explore the multiverse hypothesis, the idea that our universe might be just one of countless others. This theory suggests that beyond the observable universe, there could be an infinite number of parallel universes, each with its own unique set of physical laws and constants. While it sounds like science fiction, the multiverse hypothesis is grounded in some of the most profound theories in physics, including cosmic inflation and quantum mechanics. Cosmic inflation, the rapid expansion of the universe in the moments after the Big Bang, provides one of the strongest pieces of evidence for the multiverse. According to this theory, the universe didn't just expand, it did so at an exponential rate, creating vast regions of space that could have evolved into separate universes. These bubble universes might exist alongside ours, each with its own distinct properties. Quantum mechanics adds another layer to this idea. In the quantum world, particles exist in multiple states simultaneously until observed. Some interpretations suggest that every possible outcome of a quantum event spawns a new universe, leading to an infinite web of parallel realities. The philosophical implications of the multiverse are staggering. If true, it would mean that every possible version of reality exists somewhere. Every choice you've made, every path you didn't take, could be playing out in another universe. This raises profound questions about free will, identity, and the nature of existence itself. Are we just one version of ourselves among an infinite number of others? And if so, what does that mean for our understanding of reality? Despite its intriguing possibilities, the multiverse hypothesis remains highly speculative. Direct evidence is elusive, as these other universes, by definition, would exist beyond the reach of our observations. However, some scientists are exploring indirect ways to test the idea, such as searching for imprints of collisions between our universe and others in the cosmic microwave background radiation. Others are investigating whether the multiverse could explain why our universe seems so finely tuned for life, a question known as the anthropic principle. The multiverse hypothesis challenges us to think beyond the limits of our observable universe and consider the possibility of a cosmos far more vast and complex than we can imagine. Whether it's proven true or not, the idea pushes the boundaries of science and philosophy, inviting us to ponder the ultimate nature of reality. As we continue to explore the mysteries of the cosmos, the multiverse remains one of the most tantalizing and thought-provoking frontiers in our quest to understand the universe and perhaps the universes beyond. Now turning to the conclusion of our journey through the cosmos, let's take a moment to reflect on the incredible mysteries we've explored. From the enigmatic nature of dark matter and dark energy to the puzzling signals from distant stars and the mind-bending possibilities of the multiverse, we've uncovered just how much of the universe remains shrouded in mystery. Each phenomenon we've discussed challenges our understanding of reality, pushing the boundaries of science and inviting us to ask deeper questions about the nature of existence. These cosmic mysteries remind us that the universe is far more complex and wondrous than we can imagine. They inspire us to keep exploring, to keep questioning, and to remain curious about the vast unknown. Whether it's the search for extraterrestrial life, the quest to understand the origins of the cosmos, or the exploration of parallel universes, the journey of discovery is far from over. As we wrap up, I encourage you to stay curious and keep looking up at the stars. The universe is full of secrets waiting to be uncovered, and each discovery brings us closer to understanding our place in the grand cosmic tapestry. If you enjoyed this exploration of the cosmos, don't forget to subscribe for more deep dives into the mysteries of space. Hit the notification bell so you never miss an update, and share your thoughts in the comments below. What cosmic phenomenon fascinates you the most? Until next time, keep wondering, keep exploring, and remember, the universe is full of surprises.